Hello, I'm Mr. Aparo, and this is our three-dimensional world, an introduction to geometry for higher level students. So, I know that most of the things that we're going to be covering have already been established to you in prior grades in one way or another. But the important difference is that now that you have more knowledge about seventh and possibly eighth grade concepts, it enables us to look backwards to what we learned in fifth and sixth grade and have a better understanding than we did before. So we're going to start today by going over dimensions and how they are measured both at the one-dimensional, two-dimensional, and three-dimensional level. Now, for starters, there are three dimensions in our world. We can talk theoretically about more dimensions, but the fact is that we live in a three-dimensional world. So the dimensions that we can perceive only really go up to three. And to help me to illustrate this three-dimensional world, I brought along a little cube here that has the three dimensions taped onto it in the form of these paper strips. As you can see, we've got a red dimension, which we'll call the X dimension. We've got a blue dimension, which we'll call the Y dimension. And we've got this yellow dimension, which I made green on the screen, which we'll call the Z dimension. And these letter designations are going to be different than how you've approached dimensions in the past. But fortunately, we've been introduced to graphing and algebraic concepts, so calling them X, Y, and Z probably won't be too much of a stretch. And it'll probably help avoid a lot of the confusion that may have arisen when you were learning geometry earlier and forced to use other words in order to describe what is actually a really simple concept. So when we talk about dimensions, the most important thing to understand is that dimensions are all 90 degrees apart. They're what we call perpendicular, and that's going to be a very important word. So our three dimensions are all perpendicular from each other. And if you look at the screen here, I wrote a little note right away saying it's difficult to draw all three dimensions on a two-dimensional screen. And the reason for this is because this is a two-dimensional space. And three dimensions, it's really hard to perceive those 90-degree angles when if you're looking at it straight on with a 90-degree angle, you can't even see the third dimension at all. So we have to draw it a little bit weird like this. But don't worry, I also drew two-dimensional representations of each of the dimensions interacting with each other one. The dimensions, you might note, are just like the axes on a graph. Specifically, this first one here, we've got the x-axis and the y-axis. And you could imagine putting a graph right here. And really, this is called a Cartesian coordinate system when we're graphing. And it is possible to have a three-dimensional graph with coordinates. Perhaps maybe you could imagine a point inside this cube. We could actually pinpoint this using a set of three numbers: an x number, a y number, and a z number. So, as we just discussed, the Cartesian axes are the x, the y, and the z. The names we've been using in the past include length, width, and height predominantly, but we've also included words like base. And another one that I want you to get used to is the idea of a word called depth, which specifically refers to the third dimension. You don't really hear the word depth at all unless you're talking about three-dimensional space. So let's start with one dimension. Most measuring tools, pretty much all measuring tools, only measure one dimension at a time. And a dimension has to be straight, and the tools that we use are also straight. So we've got a ruler, for instance, or perhaps a meter stick, or we could use a tape measure. There's a number of different things that we could use in order to measure length or distance. But the fact is that when we're measuring a dimension, it has to be a straight line. The units that we might measure: inches, feet, yards, and miles for the English system, or meters, centimeters, millimeters, or kilometers for the metric system. Now, these names are going to really come into play as we move forward because you're going to keep seeing them repeated in two-dimensional and three-dimensional measurements as well. Speaking of which, two-dimensional planes or surfaces. Two dimensions put together create a 2D plane. This screen is an example of a 2D plane. It has a width and it has a height. It's two-dimensional. Even though the actual clear touch, if I were to turn it, you'd clearly see that it's a three-dimensional object. The screen itself is only two-dimensional. So, we call that a 2D plane. Or, in the case of a three-dimensional object, we call it a two-dimensional surface. A three-dimensional object could have several surfaces that are two-dimensional. A 2D measurement we refer to as an area, and it's measured in square units, which are derived from their one-dimensional counterparts. So if we take a square that is 1 foot by 1 foot and multiply them together, we end up with 1 square foot. Now, it's possible to create a measurement tool that is 1 square foot, and we could just pop it around on a surface and find out how many of them it takes to cover the surface, and that's one way to find area, or at least close to it. But the better thing, the more accurate thing that we've learned how to do is just calculate it using one-dimensional measurements and multiplication. Because when we multiply two dimensions together, we get area. It's that simple. Especially when it comes to the shape of a rectangle. Since the sides of a rectangle line up with the dimensions of a rectangle, the area of a rectangle is simply x times y, where x and y are not only dimensions, but they're also side lengths. So that was the very first thing you learned how to calculate the area of. That was probably back in 4th grade or perhaps even earlier. But in 6th grade, you learned about other areas because, of course, we don't live in a world of just rectangles. We live in a world of all sorts of shapes. But fortunately for us, we don't have to learn how to measure each of those shapes individually. Instead, we learned how to break down each of these shapes. All other shapes can be formed through combinations of the three above shapes: a parallelogram, a triangle, and a circle. Technically, you don't even need to know parallelogram. Everything can be broken down into triangles and circles if you want it to be. But parallelogram is an important first step because it helps us learn about triangles. So here we have a parallelogram, and as you notice, the formula is unchanged. It's still x times y. But remember, x and y are dimensions, not side lengths. So in the case of a parallelogram, only one pair of sides, in this case the top and bottom sides, line up with a dimension. The other pair of sides are slanted and do not line up with the second dimension. So instead, we just have to measure the second dimension as a distance across between the measured side and its opposite side. Typically, we refer to that as a height. A triangle works in much the same way. Now, there is a type of triangle called a right triangle where the sides and dimensions do line up, and so that's easy peasy. But, of course, most triangles do not have that, just like parallelograms. The important thing to note, though, is that every triangle has exactly half the area of a rectangle or parallelogram with the same dimensions. Therefore, the formula is simply x times y cut in half, or divided by 2. And that's it. If you can get the x and the y, those two dimensions, then just divide that in half and you have the area of a triangle, any triangle. Finally, the circle. 8th graders, you've already done circle. For 7th graders, you might not have gotten to it yet. But for a circle, the two dimensions are both what we call the radius, which is the distance from the center of the circle to its edge. In the case of a circle, it's the same distance no matter which direction you're going. So we have the radius length times the radius height equals the radius squared. If we take that square area and we multiply it by pi, which is kind of like the magic number when it comes to circles, then we get the area of the circle. So the formula is simply pi times the radius squared. Moving into three-dimensional space. The measurement of 3D space is called volume. Its units of measurement are cubic. In other words, they're shaped like a cube, like my little friend here. This could be considered a cubic unit of measurement. It is 1 decimeter, which is a measurement we didn't talk about, but it's 1 decimeter long, 1 decimeter wide, and 1 decimeter high. So this could be called a cubic decimeter. It also could be considered a liter, which is another metric unit of volume, which we haven't really mentioned. But as you can see, a cubic unit is simply made by multiplying all 3 dimensions together with 1 of each. So 1 inch times 1 inch times 1 inch equals 1 cubic inch, which can be used to measure volume in general in cubic inches. Same thing for, say, a mile. 1 mile times 1 mile times 1 mile is 1 cubic mile. So you can measure volumes in cubic inches, miles, cubic centimeters, cubic meters, cubic whatever. Any one of the one-dimensional units, you can slap cubic onto it, and it's measuring a 3-dimensional space rather than a 1-dimensional length. Much in the way that rectangles are the perfect shape for 2 dimensions, rectangular prisms, also known as a box, are the perfect shape for all 3 dimensions. This is because their sides line up with the dimensions. They're all perpendicular with each other. Therefore, the volume of a rectangular prism is simply the x dimension times the y dimension times the z dimension, no strings attached. However, just like with 2-dimensional, there are other 3-dimensional shapes that we need to concern ourselves with. Now, you'll forgive me for not doing many diagrams. But 3-dimensional shapes are hard to draw. So we'll start with other prisms besides rectangular prisms and cylinders as well. Since one side length lines up with a dimension, we only need to figure out what the area of the base shape is, and then all we need to do is multiply it by that 3rd dimension, since that 3rd dimension lines up perfectly. And this works for any cylinder. It works for a triangular prism, a hexagonal prism, a pentagonal prism, any prism. As long as you can get the area of its base shape, which I already told you you can, then you simply multiply it by the height. V equals B, capital B times H, and it's simple multiplication. Now, a pyramid or a cone is very similar. The only difference is that the 3rd dimension narrows to a point opposite the base, which mathematically actually just cuts the volume by 2/3. So all you need to do in order to get the volume of a cone rather than a prism, or a pyramid rather than a prism, is simply take that base, that area base, times the height, and divide it by 3. And you're done with that. So another pretty easy formula to remember. And then finally, this one I consider the hardest of the formulas to remember, the sphere formula. The radius is once again the measurement for, in this case, all 3 dimensions. So you'll notice that a component of the formula is the radius cubed. And that is where the multiplying of the 3 dimensions comes in. And once again, there's the magic pi. And then there's a fraction, 4/3. And I'm not going to go into why the fraction is 4/3. You can just memorize it. But the volume of a sphere is 4 over 3 times pi times the radius cubed. Most 3D shapes can be decomposed into a combination of prisms, cylinders, pyramids or cones, or spheres.